In this video, we begin our discussion of the topic analysis of variance. This is often referred to as ANOVA. AN, ANOVA, and then O, and then the VA for variance. Under what circumstances is it very useful to use analysis of variance techniques to analyze our data? To answer that question, let us consider a motivating example. The Chicago Connection Sandwich Company is a privately held company that operates in 4 locations in Columbus, Ohio. The vice president of sales for the company is interested in knowing whether the dollar values for orders made by individual customers differ on average between 4 locations. So, what have they decided to do? They've gone to each of the 4 locations, 1, 2, 3, 4, and they've taken a random sample of data from 8 customers each at each of the 4 locations. Our interest is to know if the location has any impact on the dollar values of the orders made by customers. In this context, it appears we would like to look at how on average the dollar values of orders vary across the 4 locations. Another way to say that is we want to see if location is a key factor in determining the variabilities in the dollar values of orders made by individual customers. So, since we have more than more than 2 groups rather, that we're talking about here, so we're testing hypotheses regarding the equality of more than 2 population means. So we're looking at the mean dollar value of orders made by customers in location 1, of orders made by customers in location 2, 3, and 4. And our interest is to see if, on average, they are the same or if, based on location, they differ. So, how many factors are we considering in this scenario? First of all, we note that the main factor we're checking if it has an impact on dollar values is location. This is called a factor in analysis of variance studies. Then, what is the response variable? Well, we're interested if the dollar values depends on location. So the dollar values of orders would be the response variable in this scenario. And of course, how many factors do we have here? We have one factor, namely what? Location. A typical question that might come with that factor is how many levels do we have for this factor? Well, how many different locations are we looking at? 1, 2, 3, 4. So we usually denote that as K, and that is equal to 4. What is the total number of measurements or data values that we've collected? For each location, we collected 8 data values. So 8 times 4, that will be 32. So N subscript T is 32. And our research question, of course, as we stated earlier, is location one of the possible factors or causes of variation in the total values of orders placed by the customers? To answer this research question, an inferential technique to use is analysis of variance. And we usually follow a number of steps, which I have outlined here on the screen. The first one being specifying the population parameter of interest. The second is formulating the null and alternative hypothesis and the level of significance. The default value in this case is alpha equals 0.05. Then to use a decision rule to determine the rejection and acceptance regions, and to collect the sample data and to compute summary sample statistics from the sample data collected and use that to test if the evidence in the sample is sufficient enough to reject the null hypothesis in favor of the alternative. And once a decision is made, we can draw an appropriate conclusion in line with the decision made. So, still looking at this question and considering the data set, our interest is to take this data set and to follow the sequence of steps outlined here in order to answer the research question. And to answer the research question, our interest is to see if location is one of the what? Possible causes of variation. That is, our null hypothesis will say that the average dollar value across location 1, 2, 3, 4 does not differ. Remember, the null hypothesis is always the hypothesis of no difference. In other words, it establishes what? Independence. Independence between location and the dollar values of customer orders. On the other hand, the alternative would be the case where at least one of these means is not what? Is not the same as all other means, which can be restated as at least one mean differs from the others. When one of these means differs from the others, then we start asking what could be the reason for the difference of one of the means from the others. That could possibly be that location is a critical factor that determines that difference in dollar values of orders. As long as this is an experiment where the principles of experimental designs are well followed, we can imply cause and effect conclusions. So, to continue, once we have stated the null and the alternative hypotheses, we would like to make a side note before we continue, and that is to consider if this is a balanced experimental design. To answer that question, let's go back to the data set collected for each of the 4 locations. Please note that each location has 8 data values. 1, 2, 3, 4, 8 each. In other words, for each of the levels, 4 levels, the same number of observations was collected. So this is a balanced experimental design in analysis of variance. So the answer here is yes, because sample size in each group are all equal to 8. The next step after noting this is to conduct some model check. There are some underlying assumptions of the ANOVA table that justify that the conduct of analysis and its overall results is valid and can carry on into the population. The first one is that all populations are normally distributed. And we'll need to check this. Usually, if most of the observations, if the data values for location 1, this seems to go from a value somewhere here, let's say around 5, to about 9. There seems to be a cluster here, and we don't see any extreme values. I don't see any dots here that would indicate any outliers. That can be sufficient or reasonable to establish what? Normality of the distribution. But that is a rough one, but is reasonable what? Acceptable. Reasonably acceptable. Then another model check is that the population variances must be equal. In this case, we tend to use Levine's test. To carry out Levine's test, we would state the null hypothesis that the variances of the groups are equal against the alternative that they are not equal. To conduct the necessary sample statistics that we need to reject or fail to reject the null hypothesis here, we can go into StatCrunch, take this data set into StatCrunch, and conduct the Levine's test on the population variances. To do that, let me do this. So I'm going to grab this, and I already have the data set in StatCrunch. And I can see the different customers, 1 to 8. and the dollar values of their orders in each of the 4 locations. With that said, let us go to stats, then we go to analysis of variance. Since we only are considering one factor, namely location, then we need just a one-way ANOVA. If we're considering more than one factor and how it bears on the dollar values of orders made by customers, then we will need 2 ways. That is coming right up. So let's go to one way, and all you need to do is grab where you have the data sets. You'll notice that the data values are under location 1, 2, 3, 4. So I'm going to click on this and then hold Control down and pick all other data values. And in this case, you will notice that I have selected columns. I've selected all 4. There are times when we can have the values in a single column. We'll see an example of that soon. So I would like to compute the Tukey HSD that is coming right up later. And I also like to conduct a test of homogeneity of variance using the Levine's test. There are other tests, but for this class, we will use the Levine's test and proceed to compute. And you have conducted your analysis of variance. So to check if the population variances are equal, I need the Levine's test of homogeneity of variance. I can see the p-value here, which is 0.9027. Since the p-value is greater than p-value of 0.9027 exceeds alpha, which is 0.05, the default value, what do? We fail to reject the null hypothesis. So we can say that the variances of the groups are equal, and that condition is met for this data set. And once that is met, then all we need to be sure of is the model check 3, where we are interested in sampled observations being independent. That is contingent on ensuring that the sampled customers are not drawn in a biased manner, that they constitute a random sample of customers at each of those locations. Then the data values must be numerical too. Okay, and once that is done, we are ready to interpret the results of our ANOVA table. Here is the ANOVA table. How did we get this? The ANOVA table will look at the different sources of variation. You see, if you go back to the data set, within each of these, within the realm of each of those populations, there are there are variabilities. So within each group, there are differences in the data values. As an overall pooled set of values, there are also differences. So the difference in these values, is it as a function of the location? In which case we would say that location is a key determinant in the differences between the average values of between the average dollar values of orders made by customers? Or is it the case that the difference is just not so significant? So in this case, when we have our ANOVA table, our interest here is to look at the different sources of variation or the different sources of differences in the other values. There will be the total source of variation. In other words, if we pull up all of those values, there will always be variabilities. And if we break it down, we will see some coming from the different locations, between the different locations, and there will be some of these variations coming as a result of the fact that it is within each location. Based on this, our interest is to see if there is enough differences coming from the samples, between the different locations, so much that it overweighs any other variation, and we can then attribute that difference to the different locations. in which case we will conclude that location makes a difference in the order values of what? Of the different customers. So take note that in this case, we will need the degree of freedom for the columns. In this case, our columns are the locations. And then you have the error. This is within samples. And in this case, our K, remember, is the different levels of what? Location. We have 4 locations. So 4 minus 1, that gives us 3. Next, we have what? The degree of freedom for within samples. That cannot be computed directly. Indirectly, it can be computed. In what way? We would need to first compute the total degree of freedom, and that would be looking at how many different values did we collect. We have 32 of them. So you have 32, 8 times 4, that will be 32 values. 32 minus 1, that will give us the degree of freedom for the total. And so as it stands, you have 31 there. And now indirectly for error, since total is 31 and the degree of freedom for location is 3, 31 minus 3 gives us 28. Then you have the sum of squares for location, we have the sum of squares for error, and we have the sum of squares total. Now the mean square error for each of the columns and the errors will be the sum of squares for columns or locations divided by the degree of freedom. That will give us the mean square error for columns or locations, and the sum of square for error divided by the degree of freedom for error. That will give us the mean square error. The F test statistic value is always the mean square for between samples or for locations divided by the mean square error, and that will give us 1.04896488. Then to get the corresponding value for this F statistic, we would use, let us see, let's go to StatCrunch again. I'm going to close out of this. We'll use the F distribution. So the F distribution is very important in working on analysis of variance. So go to statistics, go to calculators, go to F calculator, and it will require the numerator degree of freedom. That will be 3. So I have 3. Then the denominator degree of freedom, that will be 28. And then we're interested in the area above this value. So because the F distribution is a one-tailed distribution, so area above 1.04, I did this earlier. So you have this value coming right here and compute. And I have taken a picture of this and I have it right here in our notes. So you see that we have the p-value here, which is 0.3863 right here, rounded to 4 decimal places. This p-value is what I need to draw my conclusion. So this p-value is 0.3864 compared to the default level of significance of alpha. This is absolutely greater than what? Alpha. And when the p-value exceeds alpha, what do? We fail to reject the null hypothesis. If we're failing to reject the null hypothesis, let's go back to what that means. Failing to reject the null hypothesis means that these null hypotheses won, and we do not have enough evidence for the alternative that we wanted to really check. Remember, we wanted to check if location makes a difference in dollar values of orders. Since we failed to reject the null, which means the null hypothesis won, it means in this sample data, we do not have enough evidence to claim that what? Location makes a difference in dollar values of orders. So how do we write that? So we say we do not have sufficient evidence in favor of the alternative, which means we do not have strong evidence in the sample data to conclude that the only factor we're considering here, which is location, hence the use of the one-way what and over, makes a difference in the dollar values of orders. All right, let's take yet another example of this time an incomplete ANOVA table. So I am going to do this. I already have some of this pre-filled, but we're going to work it out step by step. So let's read the context first, because context is everything. It says that in a completely randomized design, 10 subjects were assigned to 4 treatments. So we have treatment 1, treatment 2, treatment 3, and treatment 4. Well, if we assign 10 treatments to each of them, 10 treatments or 10 subjects to each treatment, then at the end of the day, how many subjects do we have? We have 40 subjects here for 4 treatments, just to be clear. Excuse me there. So 4 treatments, and then since for each treatment you have 10 subjects, that means in total, if we're collecting data from each of the 10 subjects assigned to each of the 4 treatments, in total we'll have 40 values collected from all of the 40 subjects. Okay, now we would like to find the degree of freedom for treatment. Remember, this treatment has how many levels? K equals 4. So the degree of freedom would always be K minus 1, which is 4 minus 1, and that is 3. Then, what would be the total degree of freedom? I'm going to remove this 2. Remember, the total degree of freedom will be out of 40 subjects, minus 1, we have 39 as the degree of freedom for total. Then what would that of error be? Since total is 39, well, that of error will be 39 minus 6, which is 36. The next thing to do is to compute the sum of squares. We have 856.07 for the sum of squares for treatment, and the sum of squares total is 1177.97. Well, what would that of error be then? Simply subtract 1177.97 1177.97 minus 856.07. That will give us 321.9. Then, how do we get the averages, the mean squared error? Simply take the sum divided by what? By the degree of freedom, just like you do with any other mean. You take sum, you divide by number in the degree of freedom, and you get the mean square error for treatment or between treatments. And then for the mean square error for what? For the mean square error, you take sum of squared errors divided by the degree of freedom for the error. That will be 321.9 divided by 36. That is 9.4972. Then the next step is to find the F ratio. The F ratio is simply the mean square treatment or mean square between divided by the mean square error. That would give us 30.04640. And next, to get the p-value corresponding to this F ratio, we can go back to StatCrunch. And I'm going to edit this. All right, let's close out of that then. Let's go to calculators, F distribution. And what I want is, I want the degree of freedom for the numerator, 3, and the degree of freedom for the denominator, 36. So you have 3 and 36. And I want strictly the area above. The F distribution is a single tail. And above, what value? 30.04640. Oops. Let's fix that and compute. And in this case, you have 0.0000. In particular, you have 10 zeros with a decimal point after the first zero, and then 864. This is considerably lesser than 0.05. That is how I got my p-value here. And with that said, since the p-value is really, really small, that is significant. It means we're going to reject the hypothesis. What will be the null hypothesis, the null and the alternative hypothesis here? The null hypothesis will be that across the treatments 1 to 4, that they are equal, versus the alternative that at least one of the means is not equal to others. And since our p-value in this case, we just got that p-value, it is 6.5864 e minus 10. So that will be 0.000. So this will be 9 zeros. And then bring those values here, 65864. This is considerably, definitely lesser than our alpha of 0.05. Well, we can state our conclusion here. The p-value is 6.5864 e minus 10. And this is considerably less than alpha. What do? We reject the null hypothesis in favor of the alternative. That means, in this case, this means that there is sufficient evidence in the alternative. There's sufficient evidence in the sample data to conclude on the alternative that at least one mean differs from the others. Okay, and a gentle reminder that I have some spaces here just to remind us what we worked on earlier. For the degree of freedom of treatment, it is always number of categories minus 1, which was 4 minus 1, that is 3. That was the value we got right here. The degree of freedom from error always waits until we get the degree of freedom for total. That will be number of observations in total minus 1, and that was 40 minus 1, which is 39. Well, if 3 plus degree of freedom for error will give us 39, that would mean this is 36 from 39 minus 3. And next, what do we have? The sum of squared error. Let's go back again just to emphasize this. The sum of squared error would be total sum of squared minus sum of squared for treatment or between. And we work that out as 1177.97 minus 856.07 for a final result of 321.9. Let's keep that over here, 321.9. Then we have what? The mean square treatment. The mean square for treatment is always the sum divided by the degree of freedom for treatment. What do we have for the sum of squares for treatment? We had 856.07 divided by the degree of freedom, which is 3, and we got 285.3567. And similarly, the mean square error would be sum of squared error divided by the degree of freedom for error. That would be 321.9 divided by 36 from this table. And that gave us 9.4972. And to get our F ratio, we say mean square treatment divided by mean square error. What would that be? That would be 285.3567 divided by 9.4972, and that gives us 30.04640, which we used earlier to compute the p-value. So with that said, we have that complete.